Hello, everyone. Thank you for attending the CXL Consortium's Exploring CXL Use Cases and Implementations webinar. We'll begin the webinar shortly. Hello, everyone. Thank you for attending the CXL Consortium's Exploring CXL Use Cases and Implementations webinar. Today's webinar will be led by CXL Consortium member company representatives Oren Benisty from UniFabriX, Ahmed Medhioub from Astera Labs, and Matthew Burns from Samtec. Now I'll hand it off to our presenters to begin the webinar.
Thank you very much. And today we're going to explore the CXL use cases and implementations. So this is Oren Benisty from UniFabriX, and I will go over the main use cases for memory pool. But I will start, before discussing the memory pool, I will discuss the memory wall. And what is the memory wall? What we can see in this slide is a presentation of IBM at the OCP Summit a few years back, probably 2021. And what we can see in the orange bar is actually the memory channel bandwidth, and specifically the memory channel bandwidth per core. So in the green bar, we can see that the number of cores increase. So we had at 2012, I believe it was 2 core, after that 4 core, and today we are going to 64 and 128 cores. While we are discussing cores, we can see the bandwidth on the orange bar. We had 2 core with 2 channels. After that, we had 4 core with 2 channels. It means that the bandwidth was about half. And after that, we are seeing the number of cores increase, while the number of channels to the memory actually is getting flat. And the bandwidth that we can see on the orange bar means that the amount of bandwidth per core is actually decreasing. So memory pool is coming to address 2 issues. First of all, when we have fewer channels, it means that the bandwidth are not increasing at the same pace as the number of cores. And the second issue is the capacity. It means that the amount of memory that we can have per channel is limited. So we need to increase the number of channels, or we need to find another solution, external solution. The external solution comes in the form of memory pool that will provide more bandwidth and more capacity to the system. Moving to the next slide. Over here, what we can see is Meta presentation at the MEMCON event last year, and they presented their challenges, and specifically the challenges for implementing AI. And on the red color, we can see on the upper right-hand side, memory bandwidth. They showed memory bandwidth as the limitation for large language models inference. On the green bar, we are seeing the limitation as memory capacity, which is the green color, which is the recommendation engine inference. And all in all, we will look on the left-hand side and we'll see the model size that increasing from gigabyte to terabytes. All of this can be addressed by the memory pool. Now, memory pool is a tool that can provide more memory that is not dependent on the memory channel of the CPU and can provide it externally. Now, when we are looking specifically at AI models, the AI models increase their size. And when we are looking at today GPT-4, for example, this is a terabyte size of memory. And not all systems have this capacity. Using a memory pool, we can provide more memory to every host. Moving to the next slide, this is the market or the use cases that can be addressed by a memory pool. And a memory pool that we can see over here, first of all, on the bottom side, we can see private cloud and public cloud. Public cloud and private cloud both providing instances. Today, when we are buying instances, there is a specific memory attached to each core. So each representation of memory and core are correlated. In the future, when we'll have memory pool, we are able to provide memory as a service. It means that we are able, as we're increasing the number of cores, we can also, per core, increase the amount of memory. This will be a new type of memory, and we'll discuss it in the next slide. On the upper right-hand side, we can see Gen AI. Gen AI, we discuss it. We need more memory to hold the large models. The large models specifically require terabytes of memory. In a memory pool, we can hold terabytes of memory, and by that we're enabling to hold single instance with large models, and by that provide specific implementation to each use case. Other use cases can be HPC, number crunching, like national labs in the US. They require lots of memory per compute node. Animation studios, for example, they need to render lots of videos. So when you're having like 8K video, you require lots of data to hold in the memory in order to render the full video. Let's discuss medical drug discovery. Medical drug discovery, let's take, for example, DNA. DNA of a person is about a tera. You need to compare those. You need to build a full capability in order to discover and to create matching between DNA of different people. And by that, you require lots of memory. And usually, DNA sequencing is a memory-stranded application. Data analytic in high-frequency trading is having the same issues. You are having lots of data. You need to match between different databases, and by that you create memory stranded on the CPUs. All those applications that we can see in this slide actually creating memory stranding on the CPUs. All the GPUs, by the way, that will show it in the next slides. And those are the type of use cases that memory pool based on CXL will address. In this slide, what we can see is the connectivity. So CXL is actually the magic. The magic happens when CXL is connected between a memory pool and the different hosts. The different hosts are running standard Linux with standard drivers, does not require anything. It means that we are using CXL connectivity between the memory pool that we can see max memory is the product, and the different hosts are running standard Intel or AMD processors. It can be with or without the GPUs. CXL create the connectivity between the pool and the different hosts. The magic about CXL that it creates coherency between the pool and the hosts. It means that each host can see a memory as it is in the box itself. The connectivity today is CXL 1.1. Next year it will be CXL 2.0. It supports both CPU and GPUs when GPU will support the CXL. It's a standard 2U box, very similar to a top-of-rack switch. Next to the top-of-rack, you can populate it with a memory pool and provide between 4 to 32 terabytes. It means that those 32 terabytes can be shared across multiple nodes, whether it's 2, 4, 8, 16, depends on the architecture. The architecture today is limited to single system, but in the future we will support multiple boxes in CXL 3.1. CXL 3.1 will be fabric-based, and we will be able to connect multiple nodes. It means that we can scale the system to to 56 terabytes across multiple racks. The memory bandwidth can be scaled up to 512 gigabytes per second, and the whole system is capable of providing those 32 tera or in a multiple rack environment to 56 tera at very high bandwidth. Memory pooling and adaptive sharing create the opportunity both to provide the memory from a single memory pool to a single host, but we can also provide simultaneously the same memory to multiple hosts. It means that multiple hosts can address the same memory addresses, and by that we can make the system more efficient. An interesting part, we can use any media in our system. It means that we can use DDR4, DDR5, and in the next presentation from Astera, you will see that they are also presenting EDSFF. It means that it's CXL-based memory. We are also able to provide NVMe. It means storage class memory, like Intel had the Optane memory, so we are also able to present our memory as an Optane. It means that we are able to provide more capacity and persistency. It means that we are taking the NVMe and presenting it as a memory, and we're having a backup because the NVMe can be persistent. So the system is already being deployed. It means that we already have customers that buying the system and they are experimenting it to get performance, capacity, and the bandwidth. Connectivity. Today, the connectivity is based on both optical and copper wires. And in the next presentation, Samtec will present an optical connectivity between the memory pool and the different hosts. Bottom line, the system is available, and if you would like to try it, you can reach me out in this chat. This slide is actually showing the future. In the future, as we are saying, the max memory is a single box is a single appliance that is connected to different hosts. In the future, we'll be able even to connect multiple MAC systems. It means in a multiple rack environment, we are able to have multiple MAC systems and connect to hundreds of nodes altogether. So this is where we're going, connecting CPUs to GPUs, providing memory from a max memory to a multiple hosts. This environment is very, very attractive for GenNI and HPC. It means that we are having hundreds of nodes connect to many max memories that are sharing the memory between each other. This, of course, will be managed by a fabric manager that can see all hosts and all the max memories and share the memory across all nodes. Now, you are probably asking the performance. So over here, we actually have 5 different benchmarks. Those benchmarks stretching from GenAI inference, BERT, and we showed that we increased the instruction per second by 150%. In HPC, we have run HPCG, and we got 131% floating point operation per second. And those actually benchmarks can go on, and we have multiple benchmarks that show both HPC, AI, data analytics, number crunching, and we show that by increasing the amount of memory, we are able to increase the performance of almost every workload and every system. If we'll go back to the first slide that I showed, the number of cores is increasing, and it's not increasing at the same pace as the memory. By taking a memory pool, we are able to provide more memory, and each core will have more memory, and by that we'll get more performance. So the bottom line, memory pool is here. it will provide more memory to every system, and you are more than welcome to test it. My contact details are over here, so you'll have the presentation and you can send me an email. And with that, I would like to hand over to Astera.
Thank you, Oren. Hello, everyone. My name is Ahmed Medhioub. I'm a product manager at Astera Labs, focusing on our CXL Type 3 devices. To start, I wanted to sort of take a step back and talk through CXL as a high-speed, high-capacity interconnect for CPU to device or memory connections. As it is built on top of the PCIe physical and electrical interface, it includes PCIe-based block input-output protocol, CXL.io, used typically for discovery, configurations, and interrupts, as well as new cache-coherent protocols for accessing system memory. It's CXL.cache and device memory, CXL.mem. The CXL protocol defines 3 types of devices that support different combinations of CXL.io, CXL.mem, and CXL.cache protocols. The Type 3 devices specifically support both CXL.io and CXL.mem. They are typically memory expansion devices that allow host processors to access CXL device memory coherently through CXL.mem transactions for memory expansion, pooling, and sharing use cases. So some of these use cases where we see significant impact of CXL Type 3 devices fall into 3 primary camps: memory expansion, memory pooling, which Oren has went through earlier in the presentation, and memory sharing. In the memory expansion scenario on the left, the CPU is connected to multiple CXL expansion cards via a by 8 or by 16 link, expanding the total system memory capacity with additional DIMMs connected through the CXL Type 3 controller. The memory pooling use case in the middle depicts a scenario where 2 hosts connect to a CXL attached pool of memory via a Type 3 controller with 2 CXL by 8 links, allowing for a memory pool that can be statically or dynamically allocated between processing units based on demand. And lastly, a memory sharing use case where it shows host 1 and host 2 connected to CXL module via 2 by 8 links, enabling both servers to coherently access and utilize a common shared memory connected behind the controller. So the question here, what does this look like in terms of server infrastructure? Typical architecture for memory-sensitive applications, some that Oren went through earlier in his presentation, as the ones you see on the left, for example, we use 64 DIMMs via a 4-socket system. The challenge here is that you're typically buying or over-provisioning more than what you would need to run your application. For example, different extra CPUs, backplanes, drives, power supplies, etc. Versus on the right, getting 1 dual-socket CXL box with 8 by 16 memory expansion cards, for example, in 2 DIMMs per channel configuration that allows you to provision the same total number of DIMMs, 64 DIMMs. The value here is the ability to add more DIMMs without having the need for more CPUs, optimizing thus the full utilization of CPU cores while lowering both CapEx and OpEx. So the Astera Labs Leo CXL Smart Memory Controller is a Type 3 CXL 1.1 and 2.0 memory controller or memory expansion, and that's the E-series offering, as well as pooling and sharing, which is the P-series offering. The Leo CXL controller offers high-speed memory access developed through strong partnerships with leading CPU vendors such as Intel, AMD, and ARM. It is hardened through multiple interop efforts with different hosts and a growing list of DDR5 DIMM part numbers from all three major memory vendors, Micron, Samsung, and SK Hynix. The Aurora A1000 add-in card provides, a vehicle for seamless evaluation and deployment of CXL memory expansion and pooling that has gone through extensive CPU and memory interoperability and performance testing with different vendors within the CXL ecosystem, improving resource utilization, scalability, and reducing total cost of ownership. So the Leo CXL Smart Memory Controller future-proofs data centers, preparing them for the next generation of memory-intensive applications, including AI and memory databases, analytics, and others that were shown earlier by Oren. Moving on to the slide here, and I wanted to sort of highlight the problem statement that this slide describes. So looking at the left side, the volume deployment of CXL is highly contingent on multiple factors and requirements, such as applications and workloads that need to be optimized to leverage CXL attached memory. CXL attached DIMMs are part of the memory subsystem now, so reliability, accessibility, and serviceability are very important. Confidential compute as well is a strong security driver. Also, management stack and telemetry on both out-of-band and in-band need to be ready and aligned between different providers. And additionally, as I mentioned in the previous slides, CPU and DIMM interoperability are crucial for seamless integration in operations. So Astera Labs has developed a comprehensive platform solution stack to support these requirements, featuring Cosmos, which is short for our connectivity and system management optimization software. That covers all the platform APIs, modules, and embedded software running on our silicon. This stack integrates seamlessly with end applications, commonly developed community-developed device drivers, as well as OS kernel and VMCs from different vendors, and the underlying software-defined architecture of the silicon itself, enabling thus a robust and efficient CXL ecosystem. This integrated approach ensures that the CXL ecosystem is fully enabled, offering a reliable and scalable solution for modern computing needs. So to present the full view of this comprehensive portfolio of CXL solutions, first shown on the left of the slide is what is currently the most common application, that is CPU direct attached CXL memory expansion case, commonly used via CAM or EDSF. We also provide a solution for short reach CXL attached memory, usually used with cabled solutions like MXIO, depending on where the expansion module is located with respect to the motherboard and the channel loss of that connection. This is essential to unlock backplane and JBOM designs. And earlier this year, we released our new retimer smart cable modules that unlock active copper, PCIe, and CXL connections of up to 7 meters, and our optical modules for up to 50 meters. This has the potential to enable new architectures like shared and pooled memory or node-to-node, as well as rack-to-rack CXL connectivity. So if you'd like to have access to our Aurora Dev Kit or any of our products, feel free to reach out to me directly, and I'll pass it to Samtec for the next part of the presentation.
Thanks, Ahmed. I appreciate the good introduction. Appreciate Oren too. You guys did a nice job setting this table here. So the next phase that we want to consider during our webinar today is actually looking at the physical layer of implementation that a lot of the trends and use cases and topologies that Oren and Ahmed referenced. How's that actually affecting system architectures or system topologies? So there's a lot of interest in the market space for optics. So the question we're asking is CXL over optics, why the need? And this is just Samtec's perspective, but it does align with some of the things that were already presented during the webinar. Obviously, when looking at how disruptive AI has been, models are getting bigger, compute requirements are getting bigger, memory requirements are getting bigger, exponentially so. We're also seeing a rise in disaggregated computing within the data center, high performance computing, supercomputing, and the like. So when you look at these major trends within the ecosystems that CXL plays in, there's a need for more external cabling. And when you look at the use cases, we're not going to. We could spend an entire webinar detailing all the use cases here, but in general, we see three requirements or reach requirements when it comes to cabling. In the rack, typically you have to route external cabling from your chassis 2 meters plus or minus. If you're going rack to rack, the industry and a lot of the standards bodies have sort of coalesced around 7 meters of length. And then, when looking at clustering, whether that's memory clustering or GPU clustering that we're seeing, again, because of all the disruption of AI, longer distances, signal reach may be required of 10 meters or more. So the question comes up: if I need to reach 2 meters, if I need to reach 7 meters, if I need to reach 10 meters, what medium makes the most sense? And there's several industry efforts that are underway to answer those challenges. For shorter distances, depending upon protocol, there's passive DACs. We'll talk about that briefly during our presentation here. For longer distances, maybe 3-4 meters, 5 meters, there's retimed active electrical cables. PCI SIG sees the need for this. They've recently released the latest copper link cable specification, which really presents use cases for PCI Express cabling, PCI Express interconnect over twin-ax cable, using industry standard MCIO interconnect for inside the box, and then industry standard CDFP MSA solutions for outside the box that supports both PCI 5, PCI 6, or in the CXL world, CXL 2, CXL 3, 3.1. And then for some of the optical solutions for going longer distances, again, for clustering rack to rack, top of rack, or even longer solutions, you need optical. For the data rates that we're talking about, 32 gigatransfers per second at PCI 5, 64 gigatransfers per second PAM4. There's only so far that you can go with copper. So it really implies the need for longer distances that optics are needed. When we talk about optical transceiver MSAs, there's any number of form factors that the industry is looking at: OSFP, OSFP XD, CDFP, which we talked about, SFP, SFP plus. But are the optical transceiver MSAs the only form factor that is possible for routing PCI Express and, more importantly, CXL over optics? And from Samtec's perspective, we would argue that there are other options. What do we mean by that? Well, this is a highly simplified graphic that illustrates in a data center architecture or an AI system architecture where you can put the optics. a number of the solutions that we talk about will typically put the optical solutions in some sort of MSA cage with some sort of optical cable at the front panel, right at board edge. FPP stands for front panel pluggable. So that's where you're going to see your OSFPs, your OSFP-XDs, your CDFP solutions, et cetera, et cetera. On the other extreme, when looking across the data center, not just CXL, next generation data rates are looking at 224 gigabit per second PAM4 per lane or per channel. There's this thought process of CPO co-package optics. And then Samtec's perspective and where we focus in our optical solutions is onboard or midboard optics. We feel that in terms of ease of design, the density of signals that you can get, signal integrity, and the like, that onboard optics provides a path forward for a lot of the system architectures that we've talked about for CXL memory, for disaggregated computing, AI clustering, and the like. That's not to say that onboard optics makes sense for everything, and that's not to dismiss what's being done with front panel pluggables, because those are standard and will have their place. But as we go through this presentation, for some CXL use cases, using that midboard optics for point-to-point communication, memory clustering, memory architectures, memory servers, these types of approach can be very easily implemented. How do we do that? Well, Samtec, without going into all the product details, just want to hit a few of the highlights. Samtec has a growing family of midboard optical transceivers, and the illustration here shows that by placing the optical transceiver directly next to the ASIC in the system, GPU, FPGA, memory controller, whatever the case may be, you simplify the PCB layout, the signal trace from the ASIC directly to the optical transceiver. In the electrical domain, you're literally going from the ASIC pad through the PCB to the onboard PCB connector, and then entering the optical engine within that small PCB form factor. So with these onboard or midboard optical transceivers that Samtec offers, we can support up to the 32 gigabit per channel right now. Doing the electrical to optical conversion that supports PCIe 5. We're working on PCIe 6. We'll talk about that here in just a second. We also have the smallest footprint, which allows for highest density onboard systems. We'll actually show a picture of this solution here in just a moment. More importantly, our optical transceivers are protocol agnostic. Samtec has been designing, manufacturing, implementing midboard optics for the better part of 15 years. We have a long history of supporting PCI Express over optics, which we'll talk about here in just a moment. And by extension, that lends itself to CXL over optics. We'll actually show some of the proof of concepts that we have routing CXL over fiber as well. Something else that's advantageous about our midboard optical transceivers, they're very easy to attach and remove within a system. There's no through holes. It's surface mount, so you can take advantage of standard manufacturing processes. From a protocol standpoint, we've worked with customers to route Ethernet over optics, InfiniBand over optics, fiber channel over optics, specifically for this webinar, PCIe, CXL, and more. To delve into this just a little bit more detail in terms of PCIe/CXL over a physical layer optical interface, we actually have a family of optical transceivers finely tuned for the PCIe infrastructure that CXL sits on. So we have a family of PCI Express focused optical transceivers which comply with the physical layer and electrical signaling defined by PCI SIG for PCI Express enabling you to do E to O and O to E over 100 meters. We currently are working on PCIe 5. We expect to have a PCIe 5 optical transceiver midboard available by the end of 24. What's nice about these optical transceivers too is that they're scalable, they're flexible. We can support any configuration, whether that's a by 4, a by 16, a by 4, a by 8, or a by 16. We've been able to show these in CXL Solutions. Looking at the SI performance, we've seen bit error rates of better than E to the minus 12. So that's better than what's defined by PCI SIG. But more importantly for the audience on our call today, we've also been able to support CXL memory, CXL cache, and CXL IO functionality over these PCI Express focused transceivers. So not only do we have the physical layer interconnect, but we can put the CXL protocol on top of that to show CXL over optic use cases. As a matter of fact, the first time that we showed our CXL over optics proof of concept was at Supercomputing 2023 last fall. Basically, what you see on the illustration here on the right-hand side, we're using an AMD Genoa platform, which has native CXL support. Samtec designed a PCI Express form factor add-in card with our PCI Express / CXL over optic transceivers. You can see on the right that we started with a by 8 configuration because there's 2 modules. This actually is by 4 because you can see one transceiver here and another transceiver that they can plug in. And then we accessed via an endpoint a CXL device. And while we don't show it on the illustration, we're able to access memory over 100 meters of fiber, using some standard disaggregated memory point-to-point solutions. If theoretically you throw the CXL switch in here, which that's our one of the next things we want to start working on, that enables memory switching from host to multiple endpoints or from endpoint to multiple hosts as well. So we're really excited about the work that's been ongoing. We're starting to engage customers that are interested with this type of platform, and we're starting to see the advantages of CXL over optics moving forward, moving from proof of concept to reality. In addition to the optical transceivers that support both the PCI Express signaling and the CXL protocol over the PCI Express, we are designing a family of industry standard form factor PCBs, which make enabling this functionality easier for the end market user. So the current card that was in the illustration was a PCIe Chem AIC supporting PCI 4x8. We now have a solution that supports by 16. We're working on as I mentioned earlier, a PCI Express 5.0, CXL 2.0 optical transceiver that will drop into the same footprint. Hopefully, our plan is to have that available by the end of the year. The advantage of these add-in cards, highly configurable, just as we can with the optical transceivers. These add-in cards can support by 4, by 8, by 16 configurations. Do it on the same card, a single by 16 or a single by 8, a dual by 8 or dual by 4 or quad by 4. As we showed from the previous proof of concept, these can also, the same PCB can work both on the host side or the target. And we're also looking at and developing other standard form factor cards such as OCP NIC, E3.S2T, M.2, and similar for enabling CXL over optics as these system architectures continue to evolve due to AI and disaggregated computing. We talked about the density that Firefly offers in terms of its small form factor. Here we show in the circle there just one of our by 4 Firefly transceivers next to 2 QSFP-DD form factor MSAs. So we see about a 4-to-1 space savings on the PCB using a midboard optical transceiver versus front panel pluggable. Again, we're not trying to say that the midboard optics works in every application. It doesn't. But for applications where density, signal integrity, CXL operability is there. Our solutions provide an alternative to some of the things that are already available on the market. So key takeaways from our portion of the webinar: CXL over optics is a reality due to the disruption of AI and disaggregated computing within the data center, which we mentioned. We have the industry's most comprehensive portfolio of midboard optical modules, midboard optical transceivers for next-gen system architectures. And then there's some information that you can look at. You can go onto our website to get more information on our optical transceivers. You can email our optics group. And we're willing to engage on the applications that we've been talking about. So with that, we'll turn it back to Nolan, and I think he'll lead us into our Q&A.
Great, thank you. And thank you to all of our speakers for presenting today. So we'll go ahead and dive into the Q&A. If you do have any questions, please feel free to submit them into the questions box. The first question that I have is for Oren. What are the expected latency numbers for max memory? Where are the performance improvements coming from?
Okay, so latency, it's a good question. Latency, actually, we are looking at the NUMA-HOPE. It means that when you're looking at the system today in a dual socket, you have memory attached to the CPU number 0, you have memory attached to CPU number 1, and we're looking at our system as the next HOPE. It means that assume that you have like a 4-socket system, and the CPU number 2 or number 3, they have attached memory, and when we are showing the memory pool, it behaves very similar to a multi-socket platform. The improvements, again, improvement is a very good question. Everybody asks how the improvement coming to play. So the improvement of the memory pool is actually by providing more bandwidth. It means that the CPU have, whether it's Intel, they have 8 channels, or in AMD you have 12 channels to the memory. Assume that you have another channels to the memory. So the CXL is actually providing more bandwidth to the system. The other improvement is coming from the capacity. When system is designed, it's designed for maybe an average type of application that consumes specific memory capacity. But in a stranded environment, it means that you need more memory. So assume that you have in your server, let's say 2 tera, which is expensive, but actually you need 4 tera. Dynamically, in a memory pool, you can get extra 2 tera of memory from the memory pool. So you use it for a specific or for a limited amount of time, and then you return this memory to the memory pool, and other system can have it. So bottom line, providing more capacity and more bandwidth, providing the extra performance that is shown in the benchmarks.
Great. My next question is for Ahmed. What are the best practices and challenges for benchmarking and evaluating the performance of CXL solutions for different use cases?
Thanks, Nolan. I think I'll start by best practices, and I think what Oren has covered predominantly is latency measurements. I think understanding of what the target is, and as you mentioned, one NUMA-HOPE versus what are the key factors that affect that measurements and choke points in different ways, from DDR speed to width of the CXL link, that do affect that measurement. From also to add stress testing, understanding and evaluating CXL as a solution in memory pooling or expansion scenario, but under various loads to understand the behavior and see where sort of bandwidth versus capacity makes sense. And then focusing all that in terms of baseline comparison from bare metal performance between different types of memory, but also comparing it to traditional models of in these different use cases. To finally sort of understanding how properly benchmark workloads to closely mimic the actual deployment stack and actual use case. Now, the challenges here is the complexity of some of these CXL systems, and I think right now we're in better place in terms of availability as well. It's also that understanding that CXL is an evolving standards, and there is still more work to be done. Benchmarks are also sort of evolving to catch on to how to take advantage of different tiering systems, the memory tiering models, and leverage this new tier of memory. And then we have to sort of get over the integration from a challenge from the whole all the way down to the stack to the application in terms of manageability, but also as I mentioned, different ways and efficient ways to tier memory. So I think those are the overall best practices and challenges I can see, but I'm sure if Oren and Matthew have more to add to the subject.
I think you covered it. Thanks.
Great. My next question is for Matt. Does the Samtec optical cable solution include PCIe clock, sideband signals, and 3.3 VAUX?
Yeah, it does. One of the questions that we get a lot when talking about physical implementation is how do you handle the sidebands, and that's available within the solution that we have. So that's actually one of the benefits of the approach that we offer is it's quite elegant, it's quite simple to use, it's quite easy to implement from a design standpoint, and then with the ability to route the protocol, the CXL protocol over the optical PCIe link, it works quite nicely in a number of use cases. So yes, the short answer is yes to that question.
Excellent. This next question I'll share with Oren, but feel free to jump in, Ahmed or Matt. Can you share more information about the readiness of CXL technology?
Okay. So CXL technology currently, we are already build a system. We are already providing it to customers. We already have few use cases that are using the CXL. So it means that the technology is alive and kicking. From a hardware perspective, CPUs from Intel, AMD already support it. Intel supported in the previous generation of the Sapphire Rapid, and today support it with the Emerald Rapid. Next generation, of course, will support it as well. So it means that on the CPUs, we're already coming to the second generation that's supporting CXL. And because of that, it will be more deployable in the coming years, but we're already having system with our customers, so you can start testing it.
Yeah, I would just add to, we've been to a few industry events over the last couple months, and several of the key players in the memory ecosystem, not to mention anyone specifically, but several of the memory players within the ecosystem have introduced solid SSDs, memory appliances, and other solutions of the like. So I couldn't agree with Oren more that CXL is real. We're seeing adoption, and we're seeing the pieces for whether it's the hyperscalers or equipment manufacturers to really build systems that leverage the benefits and features of CXL.
Yeah, and I think the one thing I'll add on top of what Oren and Matthew said is, in terms of standardization and compliance, the CXL Consortium and work groups are way ahead, and we're now planning, the fourth and soon fifth test event with multiple vendors sort of coming together, and we can see the ecosystem growing.
Excellent. My next question is for Ahmed. Does the Leo platform provide academic support? If so, how can we access it for development and evaluation?
Yeah, so we do have offering for research, and would like we encourage and we would like to partner with any initiatives. So please feel free to contact me directly. We're slowly rolling out also an interop lab, and hopefully maybe in the future be able to have sort of access to racks in here in our lab. But until then, we can definitely collaborate with sharing hardware. So please feel free to contact me directly, and we can work on that.
Excellent. My next question is for Matt. What's the time frame for PCI 5.0 and CXL 2.0 and PCI 6.0, CXL 3.1 optical CXL interconnect from Samtec?
That's a very detailed question, but a good one and pertinent to our topic. We plan to have the PCI 5 / CXL 2 optical transceivers available late 24, early 25 at the latest. We're real excited about that. We've had some development hiccups, but stuff happens. And then we're targeting PCI 6 CXL 3.x later in 25. That's our current roadmap. Obviously, that's subject to change, but that's our plans for right now.
Great. This next question is for Oren. Performance storage systems claim low latency, optimized for the AI market. How does the memory pool based on CXL address the latency challenge?
So the latency challenge is basically physics. So in some cases, we need cable. So cable cost latency. And within the system, we are behaving like a NUMA node. So when you combine the third NUMA node and the cabling, you're getting the latency. Some of the companies provide services like memory tiering, or they can support different latencies over the memory, and by that, they're overcoming the latency issue. So latency is a challenge, but we've seen a lot of mitigation software that can address it. So it's there, but it's a solvable problem.
Great. My next question is for Ahmed. And again, feel free to jump in, Oren or Matt, if you have an answer as well. How do you foresee CXL impacting the design and deployment of in-memory databases and other AI applications?
So yeah, go ahead.
No, go ahead, Ahmed. Sorry, my apologies. You go first.
I think I can think of three major points, and I think Matthew and Oren will add to those. First, resource efficiency, and some of the points we discussed earlier in terms of memory sharing, CPU utilization, all come to play. Lower overall latency is the second one, and I think this is a crucial part in terms of optimizing the overall performance of these systems. And most importantly, I think what most of the value prop here is sort of highlighted is enhanced memory capacity and bandwidth that allows these type of systems to cache bigger and cache bigger much more data and sort of hold a larger amount of data in memory versus the old models.
Yeah, I would agree with Ahmed. To me, it's scaling, right? One of the biggest challenges that the industry is facing right now is how do you handle AI models? And I know it's, I feel like you're kind of beating on the drum, but it's saying the same thing over and over again. But it really is true, right? the AI models continue to get bigger. They continue to get larger. And, this CXL is going to be one of the tools that is available to help handle that, to, increase efficiency within the system, to lower latency, to, the cache coherency, obviously, from a system level. And, as CXL3 becomes available natively on the chipsets and more of the infrastructure becomes available, I think it's just a matter of time before the market adopts it more and more.
I would like to add to this. We have seen NVIDIA GPUs, they are already having their own proprietary solution using NVLink. CXL is an alternative to the NVLink. We've seen AMD already presented at some of the events that the next GPU will support CXL. And we've seen the whole market moving to a memory pool based on CXL, because this is not a proprietary solution, it's an actually open solution. The interfaces are standard, everything is fully available, all the information. So you will see many vendors, and when you are having many vendors, first of all, integration is easy. It's never easy, but it's doable. And second, when you are moving to a standard system, the price are going down. So you'll have low-cost interface, you will have many solutions from many vendors, both on the memory, on the interfaces, on the platform itself, management, fabric management. So all those will drive the CXL-based solution to be more commodity. And specifically for AI, this is very important, because you know how much AI system costs these days.
Excellent. I think we have time for one more question. So this one goes to you, Matt. Can you expand on what use cases may use optical CXL interconnect?
Yeah, I would. That's a $64,000 question. I think that as the optical transceiver solutions become more readily available, as there becomes more of an industry standard, the use case is really going to define the adoption. Obviously, there's a lot of optical interconnect within the data center when it comes to GPU clustering. I think we've talked earlier about how the advantage of using CXL for scaling and for latency and for a lot of the use cases that are coming out of AI. It's only going to drive adoption for CXL over optics. CXL has a ton of benefits, chip to chip on a PCB within a system, but to scale it using optics, up to 10 meters or more, I think is really going to drive it. For now, we've been able to use, Samtec has been able to use CXL over optics for type 1, type 2. We're looking at type 3. We're really anxious to see how we can use optics, in a CXL 2.0 solution when it comes to memory pooling or across a CXL switch. So I'm probably getting a little ahead of myself, but I think that the adoption of CXL over optics or CXL optical interconnect is really limitless and will be adopted more and more. Just given some of the design challenges or technical challenges that we see with AI system models and disaggregated computing.
Great. Thank you all. And thank you all for your great questions. It looks like we're all out of time for questions at this point. If we did not get to your question, we'll be developing a webinar recap blog that will address any of your unanswered questions. Thank you to our speakers for hosting the webinar. The webinar recording will be made available on the CXL Consortium YouTube channel, and the slides will be available to download on our website. Thank you.